Greetings all. This is a presentation on computing approaches for the modern software engineer that leverages principles in development and infrastructure operations, otherwise known as DevOps. The goal of DevOps is to make the software implementation process more efficient. So with that said, let's jump right in. We're going to talk about what DevOps actually is and how it ties into agile development, along with how it contrasts to the waterfall method. We will also touch on phases of DevOps, like automation testing, continuous integration, continuous delivery, along with system monitoring and analysis. These are phases that both developers and system administrators and quality assurance engineers pass through during the development cycle. We'll finally discuss some tools of the trade and setting up a DevOps environment from basic to sophisticated. Now, what is DevOps? This is when software developers, quality assurance engineers, and infrastructure or operations engineers collaboratively work together to deliver reliable software in a timely manner. Now keep in mind, this is a philosophy here. It's not the use of a particular technology, so I don't necessarily have to be using Chef or Puppet to be considered a DevOps operation when shell scripts, managing server files, and configuration can still be considered a DevOps function. So with that, let's start off with automation testing. This is conducted using test scripts based on a baseline functionality requirement to start. Obviously, the test scripts will change and increase in complexity in conjunction, or at least to keep pace with the requirements, along with the code. But the code is generally going to change more often than the test scripts. We also want to think about load and stress test, leveraging tools like Jenkins or Maven. For example, if you have a web server and a database server and you release an enhancement on your enterprise application, do you know if the CPU consumption has gone up or down in the system since the enhancement? This is where performance testing also becomes an important factor. Database testing, looking at slow queries, is another factor. Security testing, as I'm sure you're aware, is a significant issue as well. Ensuring against things like cross-site scripting and SQL injections are the basics of web application development, but there's also ensuring certain methods within certain classes are in fact private or protected, secure programming as it were. With that, we move to continuous integration. This involves automated builds involving the deployment of code files, database changes, server configuration, and UI changes. This usually begins with a commit or checking in of code into a version control system such as Git or SVN or Mercurial, thereby firing off hooks on the source control server that then fetch or retrieve the changes, push them out to the continuous integration server, build the code, and test scripts begin engaging the code. During this time, you've got a feedback loop where the tests let you know if something has failed. If so, fixes can then be redeployed and the process begins again until all tests pass, thereby taking us to continuous delivery. Now, the main difference here between what we saw in the last slide are the automated deployment and the monitoring steps in the top right, items 6 and 7. Tools like Chef or Puppet can be used in more sophisticated operations, usually large organizations with hundreds of servers. But what about monitoring these servers once everything gets to production? So deploying an application and all tests passing does not necessarily mean that all is peachy in the kingdom. While it is true you've addressed some performance tests in your automated testing phase, users can still be precarious and catch you by surprise. They do things that you never thought that they might do. These cause subtle changes in your production environment that don't crop up during testing. For example, users suddenly start uploading insanely large files because of a misunderstanding of the use of the application. This causes the CPU to work harder to retrieve data from disk, and your servers start running out of disk space. You can catch these subtleties by monitoring your system with analytics software that track its usage in production. right? As well as taking a look at different technology stacks that you might have in production, how many Java or how many Python applications you have on the enterprise system, for example. Now let's think about waterfall versus agile for a second when considering DevOps. Now, if you take a look at this, it becomes quite clear that waterfall can be difficult to justify. Why don't you pause the video and think about why that is? If you surmise that with waterfall you have to wait until the end of a lengthy cycle to perform your testing and integration and deployment, thus removing a powerful aspect of DevOps, which is continuous, you're absolutely correct. Agile makes DevOps more useful mainly because of the return on investment and its iterative nature, giving you the ability to resolve issues quickly in production. That is, having continuous testing, building, deploying, and monitoring of efforts. This saves you time and thus money, and also reduces risk. But there's a lot going on here with this aspect, right? So the main thing that we're interested in is the workflow from one environment to another, beginning with a local environment. This could be a development virtual machine with virtual environments on it, Docker images, etc. And we'll go over what all of that stuff is in a little bit. But think of this essentially as code moving from one server to another, being automatically evaluated for bugs and dependencies, and moved again gradually transitioning from being a developer's domain to an operations domain, quality assurance, etc. Remember, the whole point of DevOps is for those two domains to work cohesively together. Now, DevOps can be done by a single engineer. It's a lot of work, but it is doable. But how do we begin? Now that you have a sense of what DevOps is and how do we begin setting all this stuff up, take a moment to think about this, particularly from the perspective of what you know about software development or software engineering. And let's start by thinking about a local environment as a virtual machine, and we'll talk about the pros and cons of virtual machines or VMs. A virtual machine essentially represents many of the key hardware features of a computer: RAM, CPU, hard drive, and this is represented entirely by software as a device simulation. It's a software container that isolates the virtual device from the host system. A viable virtual machine for enterprise development should be easily deployable, such as an exported or backed up OVA file, platform agnostic, scalable, and secure. And products like VirtualBox and VMware offer these features. But why bother with VMs in the first place? Why not just dual boot your machine and have everything that you need running on Ubuntu, and then you have your Windows machine and you power off the machine and boot back up? Why not just do it that way? Why don't you pause and think about dual booting versus a VM for just a second, and we'll talk about some of the pros and cons of that. Well, one of the obvious ones, right, is you have full control over the hardware when you dual boot. Right? So if you have an 8 gigabyte machine, in the case of using a VM, and you boot up that VM with 4 gigabytes of RAM associated with it, your host machine not only has 4 gigabytes of RAM available to it. This can be an issue for some developers doing a lot of computations with their code. For example, if you're trying to train a machine learning algorithm with a fairly large data set, you're going to need all the hardware you can get. Generally, you might want to push that to a server, but say you're doing some development and testing, you want all your hardware. Now, on the other hand, it's really nice to be able to switch dynamically between operating systems on a whim. You can leverage many of the tools, software resources that are available in one operating system but not available in the other. Generally, in my opinion, my feeling is unless you're building essentially Starship Enterprise, there are few cases when a VM is not enough for development. This is what makes them quite a common software development tool that is leveraged in agile shops, leveraging DevOps in particular. We can agree that a VM is a sort of operating system container, but what about application containers? And this brings us to virtual environments, as these are such containers. These sequester computing space that is independent in terms of technology and package versions from the rest of the system. What do I mean when I say that? Well, say you have a legacy application originally written in Java 1.6, and your organization is a little reticent to modernize the application. And you need to work on some bug fixes, but your development environment at the core is set up in Java 1.9. You could use a virtual environment that will allow you to install Java 1.6, run the application in a container without disrupting your core Java 1.9 installation. A Docker image, perhaps. Same concept as a virtual machine, except that it's specific to programming environments. Another example would be virtualenv, right? Trying to build a specialized application using Python 3.0, you're not ready to commit to that, as your VM or your host machine has Python 2.7 installed on it globally. virtualenv can facilitate that. The takeaway here is that a virtual environment is an application layer, while a VM is an operating system container. Virtual environments can exist within a virtual machine or a host machine. However, virtual machines don't exist within virtual environments. More on virtual environments, in terms of some of the products that are out there, both virtualenv and Docker are fairly well established and well maintained to be considered for use. Docker is a containment management tool that consistently runs software as long as the containerization system exists, and that just means that you can't run a Docker file without Docker installed. Vagrant is another popular tool that provides consistent development environment and workflows across multiple operating systems. I encourage you to do more research on Vagrant, as the details of it aren't necessarily covered in this presentation. A little bit more on Docker. While being more system comprehensive, it's relatively young and may have issues with very heavy GUI-based applications in terms of rendering, so that's something to keep in mind. Virtualenv is a Python-specific container, so you can't really use it with Java, while Docker creates an OS-level container, allowing you to use it with any language. Now, there are a lot of tools out there. We haven't covered all of them. We've talked about essentially setting up your virtual environment, which will allow you to install a whole bunch of tools like Git, and even test and evaluate things like Docker and Chef and Puppet or Vagrant. But there are other pretty powerful tools as well, like Logstash for evaluating logs, ThreatStack for security. Not to mention Slack, which is a great collaborative tool where you can create chat threads for particular sprints and share database schemas and class diagrams, as well as code itself. CloudMap is another powerful tool for monitoring your cloud computing system. The point being, there's a lot of stuff out there, but keep in mind that the development philosophy known as DevOps is what we're primarily interested in, which is the collaboration between developers and system administrators and quality assurance folks to deliver reliable software. Thanks for watching. If you like this content, please feel free to share it or comment on it. Otherwise, by all means, stay curious.